space exploration has been a fascinating area of research and discovery for humanity.
It's one small step for man, one giant leap for mankind.
From the first man on the moon to the discovery of water on Mars, space exploration has captivated our imaginations for decades. With the launch of the James Webb Telescope, space exploration truly entered a new era of discovery and innovation. Custom-made to find and study the very first galaxies, Webb's unprecedentedly powerful infrared gaze is already delivering insights from across cosmic history, whether concerning the early evolution of the universe or the atmospheric chemistry of nearby exoplanets. Given its presently unparalleled capabilities and its price tag of more than $10 billion, some might consider the James Webb Space Telescope the one telescope to rule them all. Although it might seem that the world changed long ago from the Hubble era to the James Webb era, the reality is that humanity's greatest space-based observatory of all time is less than 2 years old. It launched on Christmas Day 2021 and required 6 months of deployment, commissioning, and calibration operations before it was ready to begin the primary phase of its life, full-time science operations. Since those milestones were achieved in July of 2022, the James Webb Telescope has been our cosmic workhorse, revealing the universe in a whole new light, with unprecedented resolution and wavelength coverage to view the cosmos. As a result, thanks to James Webb's superior power, we've come far enough to put together the broad strokes of how our universe grew up, and it's looking like a story that will lead to decades of additional research to robustly put all of the pieces together. The very first stars must have formed long before James Webb is observing, likely within a time period just 100 to 200 million years after the Big Bang. The earliest galaxies that we see are likely the brightest and most massive ones from their time, and they exist in great numbers, 500 million years after the Big Bang, and quite abundantly, even 300 to 400 million years after the Big Bang. Many galaxy candidates exist from when the universe was only 250 to 300 million years old, and there's every reason to hope that many of them will truly turn out to be confirmed galaxies once all is said and done. But when we look at these very early galaxies, we do get the impression that something is amiss. Many of these early galaxies that James Webb is finding have peculiar, puzzling properties about them that appear difficult to reconcile with this theoretical picture that the universe has painted for us. It's not that galaxies weren't forming back then, because they were, but they weren't like this. The ones spotted in this study are, as far previous research and models have told us, too red to be as bright as they are, and too bright to be as red as they are. Their bold color is what marks these galaxies as so old. As the universe expands and objects fly farther away from us faster and faster, the light they produce gets more and more stretched out. And the more stretched out light gets, the redder it looks. Objects moving towards us, on the other hand, look blue because their motion compresses light rather than stretching it out. This elongating of light is called redshift, and it's one of the ways astronomers date things in the universe. Things that are incredibly old, like these galaxies, have a very high redshift and appear bright red in observational data. But not only are these galaxies red, their brightness indicates that they're big, way bigger than they should be. Calculations done by the research team suggest that these 6 galactic candidates are each about the size of our own Milky Way, and according to almost all of our best models, there just shouldn't have been enough stuff present in the universe that early to form these things. The objects are so impossible, in fact, that according to a statement, the team has been informally referring to them as universe breakers. These galaxies disagree with about 99% of our current models of the early universe, demanding some serious reinvestigation into a matter many research thought was pretty much settled. As Joel Leja, one of the authors of the study, said in a press release, "What's funny is, We have all these things we hope to learn from James Webb, and this was nowhere near the top of the list. We found something we never thought to ask the universe. In other words, the fact that James Webb saw so many galaxies with these properties so early on is puzzling. So we're wondering, do we really understand the early phases of the formation of these galaxies? And this truly has posed a lot of questions for the theorists. The most startling explanation is that the canonical LCDM cosmological model is wrong and requires revision. As Michael Boylan Colchin, a cosmologist at the University of Texas at Austin, said, "These results are very surprising and hard to get in our standard model of cosmology, and it's probably not a small change. We'd have to go back to the drawing board." One controversial idea is modified Newtonian dynamics, or MOND, which posits that dark matter does not exist and that its effects can instead be explained by large-scale fluctuations in gravity. To date, James Webb's observations could support such a theory. According to McGaw, who is one of the idea's leading proponents, MOND has had a lot of its predictions come true. This is another one of them. However, others remain unconvinced. So far, everything that we've tried to test MOND hasn't been able to really provide a satisfactory answer, says Jehan Kartaltepe, an astrophysicist at the Rochester Institute of Technology. One simpler solution is that galaxies in the early universe could have little or no dust, making them appear brighter. This scenario could confound efforts to calculate the galaxy's true masses and could perhaps also explain ALMA's difficulty spotting Galaxies Z13. As Andrea Ferrara, an astronomer at the Scuola Normale Superiore in Italy, who has proposed such a possibility, said, "It could be that supernovae didn't have enough time to produce the dust. Or maybe, in the initial phases of galaxy formation, the dust is expelled from galaxies." Alternatively, many scientists believe that James Webb's rapid discovery of early galaxies might be testing our understanding of how these halos form, perhaps suggesting they reached an immense bulk earlier than expected. One explanation might involve the very nature of dark matter itself. Theorists have found that simple treatments of dark matter, in which it only interacts with itself and normal matter via gravity, can accurately replicate large-scale cosmic structures. But nature has no guarantee of simplicity. In reality, dark matter could interact with itself because of an as-yet unknown force, perhaps via a particle that's not in the current standard model of physics, possibly increasing the speed at which these halos grew and explaining how big, bright galaxies were able to arise so quickly. But perhaps instead, these halos were simply more efficient at drawing in regular matter to feed star formation. According to Jorge Peñarrubia, a cosmologist at the University of Edinburgh in Scotland, this is probably telling us something about how stars form in dark matter halos early on. Today, our galaxy produces roughly one new star per year, but Marco Castellano's paper based on James Webb's first data suggests that star formation rates must have been at least 20 times higher in his and Naidu's two candidate galaxies. Another Webb-derived preprint paper posits that Milky Way-sized galaxies could have arisen just 500 million years after the Big Bang, a scenario that would demand star formation rates 10 times higher still than Castellano's estimates. But according to Michael Boylan Colchin, such outsized rates of star formation stretch the boundaries of what is physically possible. If those values are correct, you'd need to have galaxies turning all their mass into stars and forming stars as fast as they could. A perhaps more plausible possibility is that stars were somehow more efficient at accumulating mass in the early universe. This would lead to bulkier, brighter stars, enhancing early galaxies' visibility to James Webb. Maybe you just create a whole load of very, very massive stars, says Stephen Wilkins, an astronomer at the University of Sussex in England. These could be so-called population 3 stars, the hypothesized first stars in the universe. Although astronomers have yet to conclusively observe such stars, there is plentiful circumstantial evidence for their existence. Emerging from the primordial hydrogen and helium gas, that pervaded the early universe, population 3 stars would lack heavier elements, allowing them to reach humongous sizes, hundreds of times bulkier than our sun. But like the brightest, briefest candles, these stars' immensity would limit their lifetime to no more than a few million years, making their detection today difficult. However, it is possible that some of the more remote galaxies already found by James Webb, and those even more ancient that may still await discovery, could contain evidence for population 3 stars. The brightness of these galaxies could be attributed to such stars, which would be much hotter and brighter than subsequent population 2 stars and population 1 stars, such as our Sun, both of which fill our modern-day universe. It's very definitely possible, says Daniel Whalen, a cosmologist at the University of Portsmouth in England. To find out for certain, James Webb will need to perform spectroscopic follow-up of these more distant galaxy candidates, a time-consuming process of gathering a rainbow-like spectrum from a galaxy's emitted light to work out which chemical elements are present in its constituent stars. One clear signature of population 3 stars, Whalen says, could be a specific spectral feature of helium that could only arise within stars that are hotter than about 100,000 degrees Celsius. That would be evidence for a massive population 3 star. What's interesting is, such follow-up observations are set to begin imminently, and it's really worth waiting. Astronomers are now racing to conduct next observations with James Webb. More programs have been designed to hunt for distant galaxies, such as Cosmos Webb, which aims to hugely increase the known population of early galaxies by observing a wider swath of sky for hundreds of hours. Future proposals might look for evidence of those first protogalaxies, perhaps using the explosive deaths of supersized first stars in especially luminous and energetic supernova as markers for their existence. Some estimates suggest James Webb could see as far as a redshift of 26, just 120 million years after the Big Bang, a cosmic blink of an eye. Much other work will be done to follow up the growing list of high redshift candidates. These would be quite amazing, at least. It would demonstrate we're not getting fooled. However, just a word of caution. It's more likely that the early universe is different from what we predicted. If James Webb finds that the apparent early burst of massive galaxy formation suddenly ebbed in subsequent cosmic epochs, this could suggest the universe was expanding faster than expected back then, perhaps twice as fast as predicted by current consensus estimates, says Nicola Menzi, an astronomer at the Astronomical Observatory of Rome. This could be linked to the influence of a particular and, so far, entirely hypothetical variety of dark energy, which is the enigmatic and mysterious force that appears to drive the accelerating expansion of the universe. So-called phantom models of dark energy allow its potency to fluctuate across cosmic time. If such models are valid, they suggest dark energy's influence on the universe's expansion could have been far greater shortly after the Big Bang than they are today. It's unsettling, isn't it? After all, such ideas, while seemingly far-fetched, cannot yet be entirely ruled out as astronomers continue to grapple with the prevalence of galaxy candidates in the early universe. At that time, having said that James Webb Telescope has ushered in a new era of science, and despite the uncertainties, the rapid communication of new discoveries has invigorated astronomers. As more data continues to pour in from the telescope, and as different teams using different observational schemes publish their results, we'll learn how to use James Webb even more efficiently and effectively. It's that glorious case where whenever we learn something new, the whole community benefits. With an expected lifetime that will take it well into the 2040s, we have decades of new science, new discoveries, and a new understanding of how the universe grew up to look forward to with great optimism. Notably, in addition to James Webb's stunning discovery, the past 12 months have seen a host of new astronomical records broken, from exploding stars to faraway black holes. 1. The most powerful light from the sun. Among the new astronomical records set in 2023 was an announcement of the highest energy gamma ray ever seen coming from the sun, an order of magnitude more powerful than had previously been seen. The sun is more surprising than we knew. Mayor Unisa, an astronomer at Michigan State University, and one of the authors who described the discovery in Physical Review letters, said in a statement, "Previously, NASA's Fermi Gamma Ray Space Telescope had detected gamma rays coming from the sun with energies up to 200 billion electron volts, or 200 giga-electron volt. That's incredibly energetic, to say the least. These gamma rays are produced when cosmic rays, which are particles from deep space moving at almost the speed of light, collide with the solar atmosphere. However, observations by the High-Altitude Cherenkov Observatory, or HAWC, in Mexico, have officially trumped that. HAWC is able to detect gamma rays indirectly. When a gamma ray photon enters Earth's atmosphere, it's bound to collide with an atmospheric molecule, smashing the molecule apart to form a shower of subatomic particles. These rain down on HAWC, which is a funny kind of telescope. It consists of 300 water tanks, each filled with 200 metric tons of water. The subatomic particles from the collision between a gamma ray and a molecule are moving so fast that when they enter water, they are actually moving faster than the speed of light, through water which is slightly slower than through a vacuum or through air. The subatomic particles produce a flash of light, a kind of visual equivalent of a sonic boom, called Cherenkov radiation. The HAWC data revealed subatomic particles that had come from solar gamma rays with energies of about 1 trillion electron volts, or 1 tera-electron volt, and a few that had energies up to nearly 10 tera-electron volt. After looking at 6 years' worth of data, out popped this excess of gamma rays, said Nisa. When we first saw it, we were like, we definitely messed this up. The sun cannot be this bright at these energies. Although the exact mechanism is still unclear, cosmic rays are thought to be responsible for these gamma rays too, penetrating 1,000 kilometers below the visible surface of the sun, where they interact with hidden magnetic fields. So, detecting these gamma rays might be able to tell us a bit about what's happening below the roiling surface of the sun. However, even though these gamma rays are the most powerful ever seen coming from the sun, they are not the most powerful ever detected from the universe as a whole. That record goes to a gamma ray detected in 2021 by China's Large High-Altitude Air Shower Observatory, which had an incredible energy of 1.4 quadrillion electron volts, or 1.4 peta-electron volts, and came from somewhere deep in the universe. 2. Vela pulsar smashes gamma ray energy record. More record-breaking gamma rays were detected in 2023, with photons pushing 20 tera-electron volt detected coming from the pulsar within the Vela supernova remnant. A pulsar is a spinning neutron star that consists of the remains of a massive star that once went boom in a supernova. Pulsars are normally detectable at radio wavelengths, but some of them also emit gamma rays, thought to be produced by electrons spiraling around the phenomena's intense magnetic field lines. The gamma ray emission from a pulsar can be illustrated as a spectrum of intensity versus energy. In most cases, these gamma ray energies run up to a few hundred giga-electron volt, above which there is a cutoff. Occasionally, a pulsar will be seen to push through this cutoff. The pulsar in the Crab Nebula has been seen to emit gamma rays that peak at 1 tera-electron volt. However, the Crab pulsar's peak has been utterly smashed by gamma rays detected coming from a pulsar in the Vela supernova remnant. The discovery was made by the High-Energy Stereoscopic System in Namibia. These gamma rays are way above the usual giga-electron volt cutoff, which implies that our understanding of how electrons are accelerated in strong magnetic fields is incomplete. 3. The universe's biggest explosion. In addition, according to new research revealed in May in the monthly notices of the Royal Astronomical Society, the most intense, long-lasting, and powerful explosion ever seen. 10 times brighter than any known supernova, and still erupting even now. was discovered in a galaxy whose light has been traveling to us for 8 billion years. Catalogued as AT2021 LWX, the explosive event was co-discovered by the Zwicky Transient Facility in California and the Asteroid Terrestrial Impact Last Alert System in Hawaii, which looks for transient events in the sky that can be anything from a moving asteroid to a flaring cosmic explosion. At its brightest, AT2021 LWX shone with a luminosity 2 trillion times brighter than our Sun. Astronomers suspect that AT2021 LWX is not an exploding star, as such explosions fade after a few weeks or months, but rather a supermassive black hole consuming a huge cloud of gas, perhaps a cloud 1,000 times more massive than the Sun itself. Astronomers call this a tidal disruption event. No such event on this scale has ever been witnessed before. The gas cloud is ripped apart by the vice-like gravitational tidal forces of the black hole, sending shock waves reverberating through the tortured cloud and releasing huge amounts of energy. With new facilities like the Vera Rubin Observatory's Legacy Survey of Space and Time coming online in the next few years, we are hoping to discover more events like this and learn more about them, said Southampton's Philip Wiseman. It could be that these events, although extremely rare, are so energetic that they are key processes to how the centers of galaxies change over time. 4. The most distant fast radio burst. A groundbreaking discovery, the most distant fast radio burst, or FRB, ever detected, was revealed in 2023. A report in the October 19 issue of the journal Science described how, on June 19, 2022, an FRB was spotted having traveled through space for a gargantuan 8 billion years. FRBs are mysterious. They are short bursts of radio waves that last mere milliseconds, yet in that short fraction of time, they can emit as much energy as our Sun does in 30 years. Nobody knows what produces them. Often they are seen to go off randomly in the universe. Sometimes they are even seen to repeat. Magnetars, which are extremely magnetic neutron stars, are the main suspect. The record-breaking burst was detected by the Australian Square Kilometre Array Pathfinder, or ASCAP, which is a group of 36 radio dishes. ASCAP pinpointed the location of the burst, catalogued as FRB20220610A, which then allowed the Very Large Telescope in Chile to follow up and identify the source as a system of 2 or 3 colliding galaxies that we see as they were 8 billion years ago. Because FRB20220610A has had to travel through so much space to reach us, it encounters lots of rogue electrons that live in that intergalactic space. The electrons steal some of the radio wave's energy, depending on wavelength, which results in the radio signal becoming slightly dispersed. The more an FRB's signal is dispersed, the more electrons it has passed through. Therefore, the measure of dispersion could tell us about hidden stores of atomic matter that are otherwise undetectable. As Ryan Shannon of Swinburne University in Australia said in a statement, "While we still don't know what causes these massive bursts of energy, the paper confirms that fast radio bursts are common events in the cosmos, and that we will be able to use them to detect matter between galaxies and better understand the structure of the universe." 5. This white dwarf is an interstellar speed demon. The fastest runaway stars ever seen speeding through our galaxy were revealed in July by astronomers poring over data of stellar motions collected by the European Space Agency's Gaia satellite. 6 new hypervelocity stars were discovered, and 2 of them, catalogued as J09276335 and J12353752, are the speediest ever seen, racing through space at 2,185 kilometers per second and 1,694 kilometers per second, respectively. To put that into context, J09276335 could orbit around the Earth 694 times in an hour, aka not quite as fast as Christopher Reeves's Superman, but still pretty fast. The stars are white dwarfs, which are the cores of sun-like stars that have stopped their intrinsic fusion reactions, puffed off their outer layers, and expired. Astronomers suspect the white dwarfs once belonged in binary systems, where the white dwarf's companion star exploded in a cataclysmic supernova, giving the white dwarf an almighty kick. According to Kareem El-Badri of the Harvard-Smithsonian Center for Astrophysics, these stars are extraordinary because they are traveling much faster than normal stars in the Milky Way. Because they're faster than the galactic escape velocity, they'll soon be launched into intergalactic space. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.